Hi, I'm Sean Powell. Welcome to the candy-coated world of calculus, Part 2. Prepare yourself for a mind-blowing calculus experience as we take you on a thrill ride through the applications of the derivative, the definition of the antiderivative, the rules of integration, the definite integral, the area under a curve, Riemann sums, and the fundamental theorem of calculus. The standard deviants are here to be your personal tutors and will take you by the hand every step of the way.
Now we know that calculus can be a really rough ride at times. The standard deviants have scoured the nation for all the introductory calculus material you need to know, and then hired some cream-of-the-crop calculus professors to help us. You can count on us to simplify this math stuff and make it easy to learn, easy to remember, and just a little bit enjoyable. Believe it, it's our job.
You have the technology at your fingertips, enabling you to pause, stop, rewind, fast forward, or slow-mo whenever you need to. We move pretty fast so that we can give you lots of calculus wisdom. If it helps you with your learning, you can take notes while we're moving along.
Also, check out the insert cards that came with the video. They've got all the secret formulas and code words we go over. They also have an outline of the topics covered, just in case you get lost, confused, or in need of some good old-fashioned structure.
Hey, you. Yeah, you. Come here. I'm the voice of common sense. Okay, here goes. To truly conceptualize the complexities of calculus, you must attend your classes, read your books, study hard, and listen to your professors. So do it. You'll be glad you did. That's it.
Part 1. Formula Review Time.
In this next brief section, we'll go over several formulas that we learned in our first video, The Candy-Coated World of Calculus Part 1. If you find this review redundant, you can fast forward until you see this big cream pie which says new stuff on it. That pie indicates the beginning of the new stuff. Get it?
Okay, here we go. The first review topic is the derivative. The derivative is fundamental to calculus. Almost everything you'll do in class and in this tape is based on the derivative, and you'll spend a lot of time learning formulas to determine it. Put very simply, the derivative is a rate of change. An example of a derivative in action is the speedometer on a car, which measures the velocity you're driving whenever you look at it. The derivative is also equal to the slope of a tangent line to a curve at a particular point, because the slope is a rate of change of y with respect to x.
What you see here is the formal definition for the derivative. The derivative of a function f, or f prime of x, equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. I know that looks a lot like a formula and not a dictionary definition, but when we talk about the definition of the derivative, that's what it is, a formula.
Today, I will be talking about calculus, with a little bit of theory of relativity thrown in. As far as calculus goes, there are several rules that help make finding the derivative easier. They are the power rule, the product rule, and the quotient rule. Let's look.
The power rule is critical, is used often, and is pretty easy. It says the derivative of a variable x raised to the power n is n times x raised to the n minus 1 power. You will get so used to using the power rule that you will be reciting it in your sleep.
Next, the product rule. The product rule says that the derivative of the product of two functions is the derivative of the first times the second plus the derivative of the second times the first. This looks like a big mess, but all you really need to do is take the derivatives of the two functions you are given and then plug everything in this formula. It's easier than it looks, trust me.
Finally, we've got the quotient rule. The quotient rule states that the derivative of a quotient of two functions is the derivative of the numerator times the denominator, minus the derivative of the denominator times the numerator, all divided by the denominator squared. Again, this looks like a worse mess than the product rule, but really, all you need to do is find the derivatives of the two functions you are given, and then plug everything into this formula. All of these rules can be found in the insert cards that came with your video.
Well, there are also two funky rules for finding some oddball derivatives that you will need to know for class at some point.
The first oddball rule was about E.
E is magic number.
E is just like pi, not the cream pie we talked about earlier, but pi, the number. E is the representation of a specific number, 2.718 ... that comes up all the time in the math world. The rule here is that if E is raised to the power of x, as you see it here, then its derivative is itself, or just e to the x. It's actually a very easy rule. The derivative of e to the x is e to the x. If only all derivatives were so easy.
The second trick rule deals with natural logs.
The natural log rule states that if f of x equals the natural log of x, then its derivative, or f prime of x, is just 1 over x. So, the derivative of the natural log of x is 1 over x.
That's it for the review. Be sure to check out your handy standard deviance insert card. It has all these rules and more right in one place. And remember, if this little review has piqued your interest and you want to find out where you can get more of the same, try checking out the companion to this video, The Candy-Coated World of Calculus Part 1.
Part 2. Applications of the derivative.
Section A, critical points.
What can I use the derivative for, you may have asked yourself? Well, the derivative has many applications. The first application of the derivative we will look at is called determining critical points.
Critical points are the points on the graph of a function where the derivative is 0 or the derivative does not exist. These are called critical points because they represent where something important is happening in the graph of the function. You'll see what we mean later. First, let's look at a picture. That's me at the Grand Canyon. Now let's look at a graph.
This is a graph. Looking at a graph allows us to speak geometrically. So, geometrically speaking, at the critical points, the tangent line is either horizontal, vertical, or it does not exist at all at the particular point. On this graph, x equals 1, 3 and 5 are critical points. At x equals 1, the tangent line is horizontal. At x equals 3, the tangent line does not exist. At x equals 5, the tangent line is vertical.
Let f of x equal x cubed minus 3x. Let's find the critical points of this curve.
The first step in finding the critical points is to, you guessed it, find the derivative. Using the power rule for each term, the derivative of x cubed minus 3x is 3x squared minus 3. Do you see how we got that?
The power rule states that if f of x equals x to the n, then the derivative of f of x equals n times x raised to the n minus 1 power. For the current expression we are dealing with, you use the power rule on each term separately to get the derivative of each term. Using the power rule on x cubed gives you 3 times x raised to the 3 minus 1, or 2. So the answer is 3x squared.
On 3x, using the power rule, you get 3 times 1 times x raised to the 1 minus 1. 1 minus 1 gives you 0 for the exponent. Anything raised to the 0 power is 1, so the answer is simply 3.
So, the derivative of x cubed minus 3x is just equal to the combination of the two answers, or 3x squared minus 3.
Next, we want to find the zeros of the derivative.
The zeros are the values of x that cause the derivative to equal 0. How do we find that?
We set the derivative equal to 0 and solve the equation for x. You can see that here. If we factor the expression, it becomes 3 times the quantity, x squared minus 1. We'll divide both sides by 3 to get x squared minus 1 equals 0. Then x squared minus 1 factors into x plus 1 times x minus 1.
We now have an expression times an expression. To solve for 0, we set each expression equal to 0 and solve for x. We get x equals negative 1 and 1. These are the x-coordinates of the critical points.
You see that? We now have the x-coordinates of the critical points of our function.
To find the y-coordinates for our critical points, we simply plug the x-coordinates we just found, negative 1 and 1, back into the original function, f of x equals x cubed minus 3x. Substituting the negative 1 in first, we get 2. So the first critical point is negative 1, 2. Next, substituting in the 1, we get negative 2. So the second critical point is 1, negative 2.
As you can see on the graph, these are your critical points. The slope of the curve is 0 at these points, negative 1, 2, and 1, negative 2, because we found the critical points by finding where the derivative was equal to 0.
And now, another example. Let's find the critical points for f of x equals x to the 2/3 power. Remember, A critical point only exists where the derivative equals 0 or does not exist. So, our first step is to find the derivative of this sucker.
To find the derivative here, we use the power rule to get 2/3 x to the 2/3 minus 1 or the negative 1/3 power. This can be rewritten as 2 over 3x to the 1/3 power. Now, to find the critical points, we have to find when this derivative is equal to 0 or doesn't exist. For the derivative to equal 0, the numerator must be 0, which it never is because it's always 2. So the derivative never equals 0. That's great because we still don't have our critical points.
Our next step is to find where the derivative does not exist. This only happens where the denominator is equal to 0, which is where x equals 0. So there is a critical point at x equals 0.
To find the y-coordinate of this critical point, we substitute 0 for x back in the original function, which is f of x equals x to the 2/3. This gives us 0 to the 2/3 power, or just 0. So the y value is also 0. So 0, 0 is the critical point.
The reason the derivative doesn't exist at 0, 0 is because the tangent line to the curve is vertical there. Remember, the derivative is equal to the slope of the tangent line at that point. Because the tangent line is vertical at 0, 0, the slope of the tangent line does not exist.
An important application of the derivative is finding the critical points of a function. How is this an application of the derivative? Well, we're using the derivative to learn something important about the function. So that's an application. Critical points are the points on the graph of a function where the derivative is 0 or does not exist. You can see this graphically by looking at the tangent lines to the curve at these points. Critical points only exist where the tangent line is either horizontal, vertical, or does not exist.
To find the critical points of a function, there are 3 main steps. First, you find the derivative of the function. Second, you find the values of x where the derivative of the function equals 0 or does not exist. And third, you substitute the x values into the original function to find the corresponding y values. You put them together and you've got the critical points.
Section B. Functions. Are they increasing or decreasing?
Now that we've looked at the critical points of a function, we can turn our attention to the behavior of the function between these critical points. That's why they're critical points, because they tell us some important things about the function. For one thing, the critical points divide the function into intervals where we can determine if the function is increasing or decreasing. A typical function has regions of both behaviors. Here's a graph that shows us what we mean by a function increasing or decreasing. The red dots on the graph indicate the critical points. Basically, a function is increasing when its graph is going upwards from left to right, and decreasing when its graph is going downwards from left to right. Pretty straightforward, eh?
Hey, voice of common sense here again. You know, this increasing, decreasing stuff is all just a matter of good old common sense. If we are looking at the graph like we read a book, from left to right, the function is increasing where the graph is going up and decreasing where the graph is going down. Enough said.
Here's how we tell whether a function is increasing or decreasing over an interval. Believe it or not, we use a derivative to find this out. If the derivative of a function over an interval is positive, then the function is increasing. If the derivative of a function over an interval is negative, then the function is decreasing.
A good way to remember what sign gives what is the pinned principle. Pin stands for positive increasing, negative decreasing. P-I-N-D, pinned. Do not attempt to find the pinned principle in any calculus classroom or textbook. It was developed by a crack team of researchers at Standard Deviance headquarters, expressly for top-secret use of viewers of this videotape.
Now, let's find where this function x cubed minus 3x is increasing and or decreasing.
The first step is to find the critical points, which we did earlier for this function. To do this, we took the derivative of our function and got 3x squared minus 3. Then, setting the derivative equal to 0 and solving for x, we found the critical points to be at x equals -1 and 1.
Now that we have the critical points, in order to find where the function is increasing or decreasing, we need to establish the intervals in which we'll look at the derivative.
The x values of the critical points divide the function into the intervals that we need to look at. So left to right, we now have 3 intervals. They are -∞ to -1, -1 to 1, and 1 to infinity. We'll see that these intervals represent where the function is behaving consistently throughout, either increasing or decreasing.
To determine if a function is increasing or decreasing, we need to check the sign of the derivative in each interval. Remember that the derivative is equal to the slope of the tangent line. Therefore, if the derivative is positive, it indicates an upward sloping tangent line, and the function is increasing. If the derivative is negative, it indicates a downward sloping tangent line, and the function is decreasing. And if you're really creative, you can draw the pattern for a really scary Halloween costume.
Wahahaha.
We can determine the sign of the derivative over a given interval by placing any convenient number within that interval into the derivative of the function. In this case, f prime of x equals 3x squared minus 3.
The first interval for this function is negative infinity to negative 1. Let's try inserting a number into the derivative equation from this interval. How about negative 5? Multiplying out, we get 72, which is positive. If we take any number from the interval negative infinity to negative 1 and substitute it for x in the derivative, we get a positive number.
Because this result is positive, from the pinned principle, positive increasing, negative decreasing, we know that the function is increasing over this interval, negative infinity to negative 1. This can be seen in this partial graph of f of x.
Now let's try inserting a different number in the same interval to prove a point.
Remember, for this interval, the number must fall between negative infinity and negative 1. Let's try negative 2. Multiply out and you get a derivative value of 9. Since 9 is positive, the function is increasing. This will hold true for any value in this interval.
The reason we can be sure that the function is increasing or decreasing just by substituting in one value is because the critical points identify the only points where the function may change direction. So, the intervals determined by finding the critical points are where the function is the same throughout, either increasing or decreasing.
The second interval is negative 1 to 1. Let's try inserting a number from this interval into our derivative equation. How about 0? Multiplying out, we get a derivative of negative 3. Based on this information, we know that if we substitute any number from that interval into the derivative for x, we will get a negative number. And as Pin tells us, a negative derivative means the original function is decreasing over this interval.
We can see this on the graph of the function. Let's add this interval to the one we established earlier. As we can see here, the function is increasing from negative infinity to negative 1, and is decreasing from negative 1 to 1. Now, let's see what happens in the last interval, from 1 to infinity.
To see what's happening in this interval, we need to insert a number from 1 to infinity. We'll use 2. Multiply it out and you get a derivative of positive 9. If we substitute any number from that interval into the derivative for x, we will get a positive number. Therefore, like the first interval, the function is increasing for x going from 1 to infinity.
If we look at the graph for the entire function, we can see that it is increasing from negative infinity to negative 1, is decreasing from negative 1 to 1, and is increasing from 1 to infinity.
Let's slow down for a second and review what we just learned. Okay, we just got some critical points. The critical points divide the graph of the function into intervals where it's either increasing or decreasing. To find out whether the function is increasing or decreasing over a given interval, we simply substitute a value from that interval into the derivative. If the derivative is positive at that value, then the function is increasing over that interval. If the derivative is negative, then the function is decreasing over that interval. To keep from mixing these up, just remember the pinned principle, that little trick we made up for you. PIN stands for positive increasing, negative decreasing. Got it? Whew. Okay, let's move ahead. Section C, the first derivative test for local extrema.
In many applications, we are not interested in where the function is increasing or decreasing, only where it has either a maximum or a minimum. In order to find this out, we need to start looking for what are called local extrema. If we put our thinking caps on, I think we can probably figure out what a local extrema is.
This graph shows us the local extrema of a function. Those big red points there, those are the local extrema. A local extrema is a point on the function where it changes from increasing to decreasing, or vice versa. Now, we're not looking at the interval where the function is increasing or decreasing as before, but at a specific point where it changes direction. Notice that a local extrema can only occur at a critical point. Not all critical points are local extrema though, but all local extrema are critical points.
For example, look at this graph of f of x equals x cubed. This is a classic example of a function that has a critical point that is not also a local extrema. The blue point here is a critical point because its tangent line is horizontal, but it's not a local maximum or minimum.
It's easy to identify local extrema when looking at a graph, but remember, you won't always have a graph. You'll need another way to figure it out. Here's how.
Remember that the derivative sign at a particular point tells us if the function is increasing or decreasing on an interval. If the derivative changes sign around a critical point, then the function has changed from increasing to decreasing or vice versa. That little point where the direction changes is the local extrema. This can also be seen by looking at the tangent lines to the curve. So in the instance where the derivative changes sign around a critical point, that means the function's slope has changed direction around that critical point.
And yet another way to identify local extrema is what you see here. When the critical points are uncovered, a mob of local extrema takes to the streets. Back to you.
There are two ways for determining the local extrema for a function. The first way is called the first derivative test for local extrema, and the second way is called the second derivative test for local extrema. A local extrema can either be a local maximum or a local minimum. We'll show you what the difference is, then we'll do some examples, so stick with us.
The easiest way to see what a local maximum or minimum is to look at the graph of a function.
Here's the function we just looked at again. The local maximums are the points highest towards the top, where the curve slopes up and then down around the point. Because the sign of the derivative or slope is changing from positive to negative. The local minimums are the points lowest on the graph, where the curve slopes down and then up around the point, because the slope is changing from negative to positive.
The first derivative test for local extrema looks at the sign, positive or negative, of the first derivative on either side of a critical point. I think you will find it very thought-provoking. It's been in all the papers.
Extra, read all about it. The first derivative test for local extrema. If the sign of a derivative around a critical point changes from positive on the left to negative on the right, the function has a local maximum at the critical point. Also, Mayor loses shirt and card game. Hot off the press.
Extra! If the sign of the derivative around a critical point changes from negative on the left to positive on the right, the function has a local minimum at the critical point. Also, Mayor loses pants in card game. So if the value of the first derivative goes from positive to negative around a critical point, we have a local maximum. On the other hand, if the value of the first derivative goes from negative to positive, we have a local minimum. Now let's look at our example function from before and find the local extrema for it.
We've already found the derivative for the function f prime of x, which was 3x squared minus 3. We also determined that the critical points are x equals -1 and x equals 1.
Remember, the critical points divided this function into 3 intervals. We found that the function is increasing from -∞ to -1, decreasing from -1 to 1, and increasing from 1 to infinity. At each place where the function is increasing, the sign of the derivative is positive, and at each place where the function is decreasing, the sign of the derivative is negative. So the sign of the derivative is positive to the left of -1, negative between -1 and 1, and positive to the right of 1.
Now we need to determine if the two critical points are local extrema. Again, if the sign changes from positive to negative, it's a local maximum. By a local maximum, we mean that at first the curve is going up or increasing, and then at the local maximum point it changes and starts going down or decreasing. If the sign changes from negative to positive, it's a local minimum. By a local minimum, we mean that at first the curve is going down or decreasing, and then at the local minimum point it changes and starts going up or increasing.
When using the first derivative test for the local extrema, it is important to test each interval around the critical point. The critical points are the key.
The first critical point is -1. Since the derivative is positive to the left and negative to the right,
The sign change indicates that -1 gives a local extrema. Since the change is from positive to negative, this local extrema is a local maximum. So, there is a local maximum at x equals -1.
The second critical point is at 1. Again, since the derivative is negative to the left and positive to the right, the sign change indicates that 1 gives a local extrema. The change from negative to positive indicates that it gives a local minimum. So, there is a local minimum at x equals 1. Section D. The second derivative test for local extrema.
The second derivative test for local extrema goes like this. If the derivative of the function at a critical point is 0, and the second derivative is positive at this critical point, the function has a local minimum there. On the other hand, if the derivative of the function at a critical point is 0 and the second derivative is negative at this point, the function has a local maximum there. Note that this sounds backwards, but it isn't. Remember, you can only use the second derivative test where the first derivative equals 0, not when the first derivative does not exist. So you can't use the second derivative test on all critical points, but only those where the first derivative equals 0.
Let's look at our same example again. This time, we'll use the second derivative test to find the local extrema of the function x cubed minus 3x. The first derivative of the function has already been determined. It is 3x squared minus 3. The second derivative is merely the derivative of the first derivative. So, using the power rule, the derivative of 3x squared is 2 times 3x to the 2 minus 1, or 6x. The derivative of 3 is 0.
Putting the two together, you get 6x minus 0, or just 6x. So the second derivative is just 6x.
Recall the derivative of our original function f of x equals x cubed minus 3x equals 0 when x is -1 and 1. So we know that -1 and 1 are the critical points, both of the applicable type for the second derivative test.
And now let's apply the second derivative test.
To apply the second derivative test, let's start substituting with the first critical point, -1. Subbing -1 for x into the equation for the second derivative gives us -6.
Since this is a negative number, the second derivative test is screaming. Hey, we got a local maximum for the original function at x equals -1. Notice that this answer matches what we got with the first derivative test earlier.
Let's continue with the second critical point, 1. Subbing in 1 for x into the equation for the second derivative gives us 6. Since this is a positive number, the second derivative test is saying, hello, we got a local minimum here for the original function at x equals 1. Again, this matches what we got with the first derivative test earlier.
You can use either the first or the second derivative test to determine any local extrema. The second derivative test is usually easier, but it sometimes backfires on us. In that loophole case, you'll need to go back and use the first derivative test. For example, when faced with a herd of madly stampeding elephants, the second derivative test does not work.
And now here's another example of where the second derivative test does not work.
If f of x equals x to the fourth, then the first derivative equals 4x cubed. Setting this equal to 0 and solving for x, we get x equals 0 as the only critical point. If we take the second derivative of x to the fourth, we get 12x squared. However, if we substitute in the x value of the critical point, which is 0, then the second derivative equals 0. Since 0 is neither positive nor negative, the second derivative test doesn't tell us if we have a maximum or a minimum here. Our only hope is to go back to the first derivative test to see if x equals 0 gives a minimum or maximum.
Now here's another example of when the second derivative test backfires.
If f of x equals x to the 4/3, then using the power rule, f prime of x equals 4/3 times x to the 1/3. Setting this equal to 0 and solving for x, we get x equals 0 as the critical point. Now, using the power rule again, the second derivative equals 1/3 times 4/3 x to the -2/3. This simplifies to 4 over 9x to the 2/3. Now, if we substitute x equals 0 into the second derivative, well...
Remember, we can't divide by 0, so the second derivative is undefined at this critical point. So again, the second derivative test backfires because we don't get a positive or negative value. We get jack squat. So in this case, we would have to use the first derivative test to determine if x equals 0 gives a local maximum or minimum.
It is usually easier to use the second derivative test to determine the local extrema, but sometimes the second derivative test just doesn't work. When this happens, you must use the first derivative test.
All right, let's review. We've spent the past few minutes looking at the local extrema, which are points on the graph of the function where the derivative changes sign. These changes can occur only at critical points. A local maximum is where the derivative changes from positive to negative around a critical point, and a local minimum is where the derivative changes from negative to positive around a critical point. To find the local extrema, there are two tests we use, the first derivative test for local extrema and the second derivative test for local extrema.
For the first derivative test, you simply test a nearby value of the first derivative on each side of a critical point. If the values change from positive to negative around that critical point, then there is a local maximum at that point. If they change from negative to positive, you have a local minimum. This is easy to visualize on a graph, where the local maximum is the high point on the top of the curve and the local minimum is the low point on the bottom of a curve.
The second derivative test is easier to use than the first, but it doesn't always help. You can use this test only when the first derivative equals 0 at a critical point. You then plug the x values of these points into the second derivative. If this value is positive, then you have a local minimum. If it is negative, then you have a local maximum. If you get 0, then you've got trouble. The second derivative must give you a positive or a negative value. Otherwise, this test doesn't help, and you will need to use the first derivative test instead. Got it? Either rewind now, or get ready for concavity.
Section E, concavity. Another tool for describing the behavior of a function that involves our friend, the second derivative, is the concept of concavity. Concavity deals with the graphical representation of a function. It's basically which direction a graph is curved, up or down.
Hello again, voice of common sense here. Although there is a more technical definition and test for determining concavity, we can talk about it first just by using common sense. Check out the following graphs.
This graph shows us a function which is concave up. How do you know? Well, just by looking at it, you can see that it's shaped like a smile on a smiley face. It's curved up on the sides.
On the other hand, this function is concave down. It looks like a frown because it's curving down.
Now here's a function with both a concave up and a concave down section. The point connecting the two is called a point of inflection.
Another way to look at concavity is the position of tangent lines to the graph.
Suppose the point c f of c is on the graph of the function, and the derivative f prime of c exists. Another definition for concavity is that... All right, get rid of those binoculars. Now let's start over. Suppose the point c f of c is on the graph of the function, and the derivative f prime of c exists. Another definition for concavity is that a function is concave up at this point, c f of c, if the function's graph is above the tangent line through that point. As you can see here, the graph is above the tangent line because the graph is curving upward.
On the other hand, a function is concave down at the point c f of c if the function's graph is below the tangent line through that point. As you see here, this function is concave down because the graph of the function is below the tangent line.
Let's look at the concave up graph again for a second to demonstrate a point about concavity and tangent lines. This function is concave up. We know that because the tangent line at this point, c f of c, is below the graph of the function. However, it could be proven that every tangent line to every single point on this function is below the graph. So the function is concave up everywhere because every tangent line to every point on the function is below the graph.
Often, a function will switch from concave up to concave down, or vice versa. As you know, the point at which this happens is called a point of inflection.
Inflection. Point of inflection. You can also look at this in terms of tangent lines. At a point of inflection, the tangent line usually crosses the graph. You will frequently find more than one point of inflection in many functions, such as this one here.
For any point on the graph of a function, 3 possible situations can occur with regard to tangent lines. The tangent line can be hanging out above the graph of the function, which would be concave down. The tangent line can be laying low below the graph of the function, which would be concave up, or the tangent line can cut across the graph, which would be at a point of inflection.
Let's look back at the old example of the function y equals x cubed minus 3x. Here, the graph is concave down because, as you can see, the graph is below the tangent line at each point. Here, the graph is concave up because the graph is above the tangent line at each point. And this is a point of inflection.
Now, on to the method for determining the concavity of a function. It's really similar to determining where a function is increasing or decreasing. To find out whether a function increases or decreases over an interval, we look at the sign of the first derivative in that interval.
To determine the concavity over an interval, we essentially need to do the same thing, but instead of the first derivative, we use the second derivative of the function. If the sign of the second derivative on an interval is positive at each point in the interval, the function is concave up. On the other hand, if the sign of the second derivative on an interval is negative at each point in the interval, the function is concave down.
This brings us to the Pund principle, a close companion to the pinned principle, and invented by the same team of crack researchers. Pund stands for positive up, negative down. P-U-N-D, Pund. The up and down refers to the type of concavity you have, concave up or concave down.
Caution! Don't get the Pund principle mixed up with the pinned principle from earlier. These two are not interchangeable. Pin tells you whether a function is increasing or decreasing over an interval. Pund tells you whether a function is concave up or concave down over an interval. Repeat, the two are not interchangeable.
Here are the basic steps for determining concavity. You must first find the second derivative of the function, second, set the second derivative equal to 0, and find the values which satisfy the equation, and third, once we have these values, then we test what is happening around them, just like we did to determine if a function is increasing or decreasing.
To test these values, we look at the intervals immediately to the left and right of them. Again, if the second derivative is positive in an interval, the function is concave up in that interval. If the second derivative is negative in an interval, the function is concave down in that interval. Just remember Pund, positive up, negative down, and you'll be set. Also, if the function changes from concave up in one interval to concave down in another interval, or vice versa, we know there's a point of inflection at the point in between the intervals.
Okay, one more time. Let's look at our example from before. Let's determine the concavity of the function x cubed minus 3x. Also, let's determine if there are any points of inflection. Previously, we found the first derivative to be 3x squared minus 3, and the second derivative to be 6x.
Now we need to find the values of x that make the second derivative equal 0 or not exist. Setting 6x equal to 0, we get x equals 0.
So 0 is the only value that makes the second derivative equal 0. Based on that knowledge, we can establish the intervals for the example. The intervals to the left and right of 0 are negative infinity to 0 and 0 to infinity.
Now we'll plug in convenient values from each interval into the second derivative to determine whether the function is concave up or concave down in that interval.
From the first interval of negative infinity to 0, let's plug in negative 1. That's between negative infinity and 0, isn't it? This gives us 6 times negative 1, or negative 6. Remembering Pund, positive up, negative down. We know that the original function is concave down on this interval since we got a negative answer. Here's what this interval looks like on the graph.
For the second interval from 0 to infinity, let's plug 1 into the second derivative. That's between 0 and infinity, isn't it? Well, plugging this in gives us 6 times 1, or 6. Again, remembering Pund, the original function is concave up on this interval because we got a positive answer. Now let's add this interval to the graph.
Now, since the concavity switches from concave down to concave up, we know there is a point of inflection somewhere. X equals 0 is where the concavity switches, so that's where the point of inflection is. Since this is the only place where the concavity switches, this is our only point of inflection. Section F, some sample minimum maximum problems.
Here's our first example. It comes highly recommended by doctors and pharmacists. Suppose we want to find the minimum, if there is one, of the function f of x equals x times e to the x.
E to the x. E to the x. Let me tell you about e to the x. All right, you tell him.
Now, don't forget the basic rule about e to the x. E is just another way of saying 2.718 ... And whenever e is raised to the x, the derivative of e to the x is just e to the x.
Well, to do this problem, x times e to the x, step 1 is to compute the derivative, which is found by using the product rule, because you've got two functions here multiplied by each other. Remember the product rule? It's the derivative of the first function times the second function plus the derivative of the second function times the first function.
Here, the first function, g of x, is x, and the second function, h of x, is e to the x. The derivative of the first is g prime of x, which equals 1 times x to the 1 minus 1, or 0 power, which is 1. And the derivative of the second is h prime of x, which equals e to the x. Remember, the derivative of e to the x is just e to the x. So, the derivative of f of x is equal to the derivative of the first, which is 1, times the second, or e to the x, plus the derivative of the second, which is e to the x, times the first, which is x. To simplify this, we can factor an e to the x out of each term. After doing this, we're left with the quantity of 1 plus x times e to the x. So, the derivative of f of x equals x times e to the x is f prime of x equals the quantity of 1 plus x times e to the x.
Step 2 in finding the minimum of this function is to find the critical points.
To find the critical points, we find where the derivative is 0. The first part, 1 plus x, is 0 when x equals negative 1. So, negative 1 is a critical point. E to the x is never 0, because as you know, e is always equal to 2.718 ... and it's raised to a power. Any positive number raised to any power can never be 0. So, x equals negative 1 is the only critical point.
Now to determine if x equals negative 1 is a minimum or a maximum, we can try the second derivative test. So, step 3 is to find the second derivative, which we do, again, with the product rule, because the derivative of the first function, f prime of x, ended up being the product of two functions.
Okay, hold on to your hats, here we go again. Remember the product rule? If not, pull out your insert card and follow along. When finding the derivative of f prime of x equals the quantity 1 plus x times e to the x, g of x is 1 plus x, and h of x is e to the x. So, g prime of x is then the derivative of 1 plus x, or, using the power rule, 1. And our h prime of x is the derivative of e to the x, which is, say it with me, e to the x. So, f double prime of x equals the derivative of the first, which is 1, times the second, or e to the x, plus the derivative of the second, which is e to the x, times the first, or 1 plus x.
Okay, so here's what we got. Now we can factor this sucker. There's a common factor of e to the x that can be pulled out. This gives us the quantity of 1 plus 1 plus x times e to the x. This then simplifies to the quantity of 2 plus x times e to the x. That's the second derivative.
Now that we have the second derivative, the next step, or step 4, is to substitute the critical value into the second derivative to see if that value gives a minimum or a maximum. What's the critical value? That's just the value that we found earlier in step 2, which was x equals negative 1. Subbing in negative 1, this gives us 2 plus negative 1 times e to the negative 1. This simplifies to 1 times e to the negative 1, which simplifies to e to the negative 1. And finally, another way of writing e to the negative 1 is 1 over e, which is just 1 over approximately 2.718. Well, 1 over 2.718 is positive. So remember, if the second derivative is positive, then the critical point is a minimum. So x equals negative 1 gives a local minimum.
Now, the final step, or step 5, is to find the corresponding f of x or y value of the minimum.
To do that, you substitute x equals negative 1 back into the original equation. Did you hear that? Into the original equation, or f of x equals x times e to the x. Substituting gives you negative 1 times e to the negative 1. This simplifies to negative 1 over e, or negative 1 over about 2.718, which approximately equals negative 0.367.
So, the minimum of the function f of x equals x times e to the x occurs at the point negative 1, negative 0.367.
To confirm our conclusion, we can look at a calculator-generated graph of the function. You can see that this point is the low point on the graph of the function. We must have done something right. Yay us!
Now we can move on to some more applications of the derivative. Finding the maximum and minimum values of a function are problems that will often come up in your calculus studies. Just to make things more real, we're now going to do a word problem.
Okay, everybody calm down. When approaching a word problem, the key is to look at what you're given and proceed along slowly, using what you've learned.
All right, here it goes. Let's say that your Uncle Skippy decides to go into business for himself. He has a great idea that he sure will be $1 million seller. His idea is a new product called Uncle Skippy's Premium Edible Dirt.
Uncle Skippy, just like any good entrepreneur, is concerned about the cost of overhead. He wants to sell 32 cubic inches of edible dirt in each package and needs to have a box with a square base for shipping purposes. Skippy also wants to save money on edible dirt boxes by conserving the amount of cardboard used to make each box. Right now, he has 3 different size boxes that will contain exactly 32 cubic inches of edible dirt. One is 32 inches by 1 inch by 1 inch. The second is 8 by 2 by 2. The third is 2 by 4 by 4. None of the boxes have tops because Uncle Skippy plans to put a special freshness seal on the top.
While all 3 will hold 32 cubic inches of edible dirt, the boxes are all different sizes, so they each have different surface areas. But which has the smallest surface area and therefore costs the least to produce? And furthermore, once that is determined, is there any other size box out of all possibilities that will minimize the amount of cardboard needed for each one?
So our word problem looks like this. Uncle Skippy wants to sell his premium edible dirt in quantities of 32 cubic inches per box. He wants to keep his packaging costs as low as possible, using as little cardboard as necessary per box. So part A. Of the 3 sample boxes given, calculate which has the lowest surface area, and part B, calculate the minimum surface area possible for a box with a square base to hold 32 cubic inches of premium edible dirt.
Now, the way to tackle this is to first determine the surface area of each of the 3 given boxes to get the answer for part A. Then, use calculus to determine the minimum surface area, or the least amount of cardboard needed to make a box with a square base that holds 32 cubic inches.
To figure this out, Uncle Skippy cuts up the boxes and spreads out all their sides. He then measures the sides and computes the area of each cut-up box. Remember, box number 1 is 32 inches by 1 inch by 1 inch. Box number 2 is 8 by 2 by 2. And box number 3 is 2 by 4 by 4. And none of them have tops.
What's the surface area of each box? Well, let's come up with a formula for surface area that we can apply to each box. Let's call the length of the box x. Since the box has a square base, the width of the box is also x. We'll call the height of the box y. Since there's no top on each box, the surface area equals the areas of the 4 sides plus the area of the base. Because the base is x by x, the area of the base is just x squared. Also, each side of the box is x by y because y is height. So the area of each side is xy. There are 4 sides, so the area of all 4 sides is 4xy. Thus, the total surface area is just the area of the base plus the area of the 4 sides. The formula would look like this. Surface area equals x squared plus 4xy. For box number 1, x equals 1 and y equals 32. So plugging in, s equals 1 squared plus 4 times 1 times 32, or 129 square inches.
For box number 2, x equals 2 and y equals 8. So for box number 2, s equals 2 squared plus 4 times 2 times 8, or 68 square inches.
For box number 3, x equals 4 and y equals 2. So for box number 3, s equals 4 squared plus 4 times 4 times 2, or 48 square inches.
Therefore, box number 3, which is 4 by 4 by 2, has the smallest surface area, 48 square inches, and thus requires the least amount of cardboard of the 3.
Okay, so now we know that of the 3 boxes, this one has the smallest surface area. But is it the smallest box with a square base that can hold 32 cubic inches of premium edible dirt? Uncle Skippy wants to be sure that it is. If it's not, then he wants to know if there's an even better box out there, which will hold 32 cubic inches of premium edible dirt.
So now we get to the calculus. Uncle Skippy is essentially asking us to minimize the amount of the cardboard needed to make the box. So this problem is asking for the minimum surface area that will hold 32 cubic inches of edible dirt.
That's premium edible dirt.
We've already determined that the formula for the surface area of a box with a square base and no top is x squared plus 4xy. This is what we want to minimize. We don't know what size box we need, but we do know that the volume must be 32 cubic inches. So, we need to put the volume in terms of x and y so we can solve our problem. The formula for the volume of a box is just the length of the base times the width of the base times the height of the box. Since we're looking for a box with a square base, the formula for this problem is just x times y, or x squared y. We know that this is equal to 32 cubic inches because that's the volume Uncle Skippy wants.
Remember, 32 cubic inches is the amount of dirt I want my box to hold.
The surface area equation, which is what we are looking to minimize, is a function of more than one variable. S is expressed at a function of both x and y. What we want to do then is substitute something for y into the surface area formula that is in terms of x. To do this, we'll use the volume formula.
Since the volume is 32 cubic inches, we'll let x squared y equal 32. Now we can solve for y by switching the equation around, then dividing both sides by x squared. We get y equals 32 divided by x squared.
Now, let's plug it in.
So, let's plug 32 over x squared into the surface area formula where we see the variable y. This will give us a function with only one variable, x. Plugging in 32 over x squared for y, we get the surface area function equals x squared plus 4x times 32 over x squared. This simplifies to s, or f of x equals x squared plus 128 over x. So now we have a function that's in terms of x only, and we can use it to help us solve the rest of the problem.
Remember, our goal is to find the minimum surface area for a box to hold 32 cubic inches of edible dirt. We can solve this problem the same way we did the minimum problem earlier. Now let's review the top 5 steps for solving a minimum-maximum problem. Here we go.
The top 5 steps for solving a minimum-maximum problem are: Step number 1, find the derivative. Step number 2, find the critical points. Step number 3, find the second derivative. Step number 4, apply the second derivative test. And the fifth and final step for solving a minimum-maximum problem is find the corresponding f of x value.
So, step 1 is to find the derivative. The surface area function equals x squared plus 128 over x. To help us find the derivative, we can rewrite this as x squared plus 128 times x to the negative 1. Now we can take the derivative of this using the power rule. The derivative of x squared is 2x, and the derivative of 128 times x to the negative 1 is negative 1 times 128 times x to the negative 2. This simplifies to 2x minus 128 divided by x squared. You know what that means. It's time for step 2, which is to find the critical points.
To find the critical points, we set the derivative equal to 0 and solve for x. We first need to multiply each term by x squared to get rid of the fractions. In the first term, x squared times 2x is 2x cubed. Then, the x squareds cancel out, and the x squared times 0 in the last term is 0. Next, we add 128 to both sides of the equation. Finally, we divide both sides by 2, so we get x cubed equals 64. X equals the cube root of 64, or 4. This is the x value of our critical point.
Wait a minute. We have a critical point. But that critical point could be a minimum or a maximum. Uncle Skippy's problem calls for a minimum, so we need to determine which it is. How? We could either use the first derivative test or the second derivative test. The first derivative test is more time-consuming. The second derivative test is not always conclusive, but it's easier. Let's try the second derivative test first. And if that doesn't help, we can go back and use the first derivative test. Let's do it.
So, step 3 is to find the second derivative of our function, x squared plus 128 over x. We already found the first derivative of x squared plus 128 over x, which is 2x minus 128 over x squared. Remember, to find the second derivative, just take the derivative of the first derivative. We can do this term by term.
The derivative of 2x is just 2. For the derivative of negative 128 over x squared, first rewrite it as negative 128x to the negative 2 power. Using the power rule, you get negative 2 times negative 128 times x to the negative 3 power. We can rewrite this as 2 plus 256x to the negative 3, or 2 plus 256 over x cubed. So that's the second derivative. Now we're ready for step 4, which is to apply the second derivative test.
Now that we have the second derivative, we just need to plug in x equals 4, which was the x value of our critical point, to find out if our critical point gives a minimum or a maximum. Well, here goes.
So, step 4 is to apply the second derivative test by plugging in our critical point x equals 4 to see if we get a positive value or a negative value. Plugging in, we get 2 plus 256 over 4 cubed. This equals 2 plus 256 over 64, which simplifies to 2 plus 4, or 6. Remember, if the second derivative is positive at the critical point, then the function has a local minimum there. Since 6 is positive, x equals 4 gives a minimum.
You could also graph the function x squared plus 128 over x as we've done here. You can see that at x equals 4 there is a minimum value because it is the low point of the curve.
Alright, so now we know x equals 4 gives us a minimum. But what's the other dimension? What's the minimum surface area?
Well, now we know that x equals 4 gives a minimum. So the last step is to get the height, or the y value, that goes with x equals 4 into the volume equation. This is different from the equation we found the derivative of, but the volume formula gave y in terms of x. So we go back to that relationship and plug in x equals 4.
Since x equals 4, we'll plug that into the volume formula, which was x squared y equals 32, to get the height of the box at the critical point. So y equals 32 over 4 squared, which equals 2. Remember, x is the length and width, and y is the height. Therefore, the dimensions of the best box for Uncle Skippy are length and width of 4 and height of 2, giving a surface area of 48 square inches. It just so happens that this was also the smallest of the 3 boxes that we started with. But now we are sure that this box has the minimum surface area possible to hold 32 cubic inches.
So my box should have a length and width of 4 and a height of 2. Now I'm ready for the big time.
Section G, derivatives in distance, motion, velocity, and acceleration.
Derivatives have other cool applications, such as helping us describe and analyze different types of motion. You probably learned some basic ways to compute motion in other math classes, but with calculus, we take it a step further. For example, let's say that you're in your brand new VW Beetle and have just left your house and are heading towards Grandma's with some hot cross buns. Now, we can determine your speed with the trusty old formula, velocity equals distance over time, or v equals d over t. If you left at noon and arrived at 2 p.m. and Grandma lives 150 miles away, then your average velocity was 150 miles over 2 hours, or 75 miles per hour. The problem with this type of calculation is that it only gives you the average velocity over a period of time, and not the instantaneous velocity at a specific moment in time. Let's say we wanted to know your instantaneous velocity 1 hour after you left. Without calculus, we can't do it. Thank goodness for calculus.
E is the magic number.
Please ignore this interruption. E has nothing to do with what we're talking about in this section of the tape, but our writer ran out of ideas. We apologize for any inconvenience this may have caused. Thank you.
Now let's see what calculus can add to our VW example. Let's look at your Beetle again as it leaves your house on the way to Grandma's. We can describe its motion with a function called a position function. The position function is represented by s of t, with t being time and s being the symbol for distance, or more precisely, position. Why s? Well, with the derivative, we eventually get kind of overloaded with d's, you know? du, dx, dy over dx, and so on. So instead of d for distance, we use an s, which is the next best thing. The position function is a measure of where you are at any given time. So at time t, you are in position s of t.
So in official calculus terminology, calculana hookah maka hui. Oh, I'm terribly sorry, that was gibberish. In calculus terms, a function representing the position of an object along a line with respect to time is called the position function. The position function is sort of a measure of distance because the object is moving over time, and it's got to be moving somewhere.
Okay, so we have a position function s of t. Now the derivative of the position function is the instantaneous velocity, and it's called the velocity function. It's represented by v of t, so v of t is equal to s prime of t. The velocity is what we often think of as speed, you know, like 75 miles per hour.
The standard deviants do not endorse traveling in excess of 65 miles per hour. Unless, of course, you're being pursued by a herd of stampeding elephants, in which case speeds upwards of 120 miles per hour are highly recommended.
We do make a distinction between velocity and speed, though. Speed only tells us how fast something is going. Like you're in your Beetle and you're going 75 miles per hour. But what if you turned around and were going 75 miles per hour back toward your house because you forgot the hot cross buns for Grandma? Well, your speed is still 75 miles per hour, but your velocity would be negative 75 miles per hour because you had reversed your direction. The velocity also tells us which direction you're going, forward or backward. So, to be exact, the speed is the absolute value of the velocity.
Now, if we want to go a step further, the derivative of the velocity function represents the instantaneous acceleration and is called the acceleration function. Since the acceleration is a derivative of the velocity, it's the rate of change of the velocity. So acceleration is the rate at which an object is speeding up or slowing down. The acceleration function is represented by a of t. Note that this is the first derivative of the velocity function and the second derivative of the position function.
Okay, so one more time. S of t is the position function. The derivative of s of t equals v of t, or the velocity function. And the derivative of v of t, which is also the second derivative of s of t, is the acceleration function, a of t. Now, all of these functions have a t in them, so all of them are with respect to time. If the velocity is positive, then the position is increasing with time. But if the velocity is negative, the position is decreasing with time. If the velocity is 0, the object is stopped, so the position remains constant with time.
Similarly, if the acceleration is positive, then the velocity is increasing with time. While if the acceleration is negative, the velocity is decreasing with time. If the acceleration is 0, the velocity remains constant with time.
The same thing happens with the derivatives of bunnies. If the bunny is positive, then the bunny is increasing with time. If the bunny is negative, then the bunny is decreasing with time. If the bunny is 0, the bunny remains constant over time. As long as you remember to refill pellets and keep a fresh supply of water available.
All right, let's do a problem. And please bear in mind, word problems like this one are set in a hypothetical world to make a point.
It appears that Uncle Skippy's premium edible dirt business has taken off. He is expanding into the edible dirt dumpling delivery biz. His delivery man is his son Flip, who bears an uncanny resemblance to Uncle Skippy. One day, Uncle Skippy gets an order for a piping hot batch of premium dirt dumplings to be delivered to the plutonium factory down the street. And those plutonium workers don't like to be kept waiting, if you know what I mean.
Our man Flip is on the job. He checks the address, takes off out the door, gets a bit down the street, and then realizes he forgot to bring the premium dirt dumplings. Undaunted, our man Flip stops, runs back home, gets the dumplings, and boogies back down the road to the factory. This all takes place in about 5 seconds or so. Did we mention that his alias is Super Flip?
Let's say, for the sake of the example, that the graph of Flip's path that morning can be seen as the function s of t equals t cubed minus 6t squared plus 9t. So, t cubed minus 6t squared plus 9t is the position function.
Here is a graph of the function. We can see on the graph that t, or time, is measured in seconds, and s, or distance, is measured in feet. The height of the graph is the distance Flip is from home at time t. We can see from this graph that at time t equals 0, Flip is at home, so s of 0 equals 0. Flip then leaves home the first time, remembers the dumplings, and turns around to go get them at t equals 1. Then here he's back at home getting the dumplings at time t equals 3. Finally, he boogies off to go deliver those premium dirt dumplings to the plutonium factory.
For our problem, let's say we want to find Flip's velocity and acceleration after a certain period of time. Since we know Flip's whole trip lasted 5 seconds, let's find his velocity and acceleration at the end of 4 seconds.
The first part of the problem is to find Flip's velocity. We know that the velocity is the derivative of the position function. So, to get the velocity, we merely need to take the derivative of the position function. Using the power rule, we see that the derivative of the position function is 3t squared minus 12t plus 9.
The first part of the question asks for Flip's velocity after 4 seconds. To find this, we merely let t equal 4 and then plug 4 in for t into the velocity function. Remember, the velocity equals the derivative of the position function. This will give us Flip's velocity after 4 seconds.
Plugging 4 in for t in the velocity function gives us a velocity equal to 9. Since our unit of measurement is feet and seconds, Flip's velocity is 9 feet per second.
The second part of the problem asks us to find Flip's acceleration after 4 seconds. To find the acceleration, we need to take the derivative of the velocity function or the second derivative of the position function.
Since the velocity function equals 3t squared minus 12t plus 9, the derivative of the velocity function is 6t minus 12. This is also the second derivative of the position function. So, we used the power rule again, but this time on the velocity function, to get the acceleration function.
To find Flip's acceleration after 4 seconds, we merely let t equal 4 and plug that into the acceleration function.
Substituting 4 for t gives us 12. Once again, the units are measured in feet and seconds, but since this is acceleration, we use seconds squared. So Flip's acceleration at 4 seconds is 12 feet per second squared.
By the way, since Flip's acceleration is positive at 4 seconds, we know that he's speeding up at that point, so his velocity is increasing as well. If Flip's acceleration were negative, his velocity would be decreasing and Flip would be slowing down. If we want to find where Flip has stopped moving completely, we just need to find the points where his velocity equals 0. Remember, the velocity function is the derivative of the position function. So, finding the zeros of the velocity function is just like finding the critical points for the position function. Get it? Let's do that now for Flip.
The first step is to set the velocity, or the derivative of the original function, equal to 0. 3t squared minus 12t plus 9 equals 0. This factors into 3 times t minus 3 times t minus 1. So at t equals 1 and t equals 3 seconds, Flip has stopped moving because his velocity is 0. Now we know that at 1 second, Flip stopped and remembered the dumplings, and at 3 seconds, Flip has stopped at home picking them up.
Let's try one more example. For this one, we're given that s of t, or the position function, equals negative 16t squared plus 96t plus 6.
This happens to be the height of a hard-boiled egg thrown vertically upward at 96 feet per second by a chicken from a point 6 feet above the ground. We want to determine how high the egg will reach.
When the egg is at its highest point, the velocity will be 0 because the egg will stop moving before it switches direction and comes back down. So, we need to get the equation for velocity and then find where it equals 0.
Remember, the velocity is just the derivative of the position function s of t. So the velocity equals the derivative of negative 16t squared plus 96t plus 6. Working the math with the power rule, we get that v of t, the first derivative of s of t, equals negative 32t plus 96.
Okay, so now we have the velocity function for the egg. Remember, we want to know how high the egg goes up in the air. Since the velocity of the egg at its highest point is 0, we need to set this expression equal to 0 and solve the function for t. So 0 equals negative 32t plus 96. Bring negative 32t over to the other side and divide the 32 out. So t equals 3. Since t is measured in seconds, t equals 3 seconds. 1, 2, 3.
Now, we know that it takes 3 seconds for the egg to reach its maximum height and stop going up.
We still have not answered the question, though. The question asks for a height. How high is that egg at 3 seconds? What we are really looking for here is the position of the egg at 3 seconds, since we have determined that it's at its highest point at 3 seconds. We use the position function to get this information. Now, we simply substitute in the value of t for the time it took for the egg to get to its top height. So we substitute 3 for t in the position function to get the final answer. When we substitute 3 in for t into the position formula, we get 150 feet. So that's our answer.
So now you've seen how the derivative can apply to word problems, such as minimum, maximum, and position function problems.
Part 3. The antiderivative and the definite integral.
As you have seen, derivatives are an essential part of calculus because there are so many different applications that they apply to. Another big, huge, importantly essential part of calculus is the antiderivative.
Section A, the definition of the antiderivative.
The antiderivative is basically the opposite of the derivative, just like division is the opposite of multiplication. For example, say that you are given the position function for a spaceship orbiting the Earth. We could use the derivative to find its velocity and acceleration. On the other hand, what if we were only given its acceleration? Well, then we could use the antiderivative to find its velocity and then its position. So you can see that the derivative and antiderivative are closely related, but are essentially opposites of each other.
Here's a weird fact for you. Every single derivative has an antiderivative. Every single one. In fact, there are an infinite number of antiderivatives for each one derivative. We'll explain.
Here's Bob Cowpoke McIntyre. He's a dreamer. Here he is running along chasing his dream, which is just out of his reach. Ever since he was a child, he's wanted to be a cowboy, but he grew up and became a nuclear physicist. For this example, at time t, Cowpoke, as his friends call him, is a distance of t squared from home. So at time t equals 0, he is at home. After 1 second, he is 1 foot from home. After 2 seconds, he is 4 feet from home. After 3 seconds, he is 9 feet from home, and so on. So, Cowpoke's position function is s of t equals t squared, which will give us his distance from home.
However, his speed, or velocity, is given by the derivative of t squared, which, by the power rule, is 2t. As we see, his velocity at time 0 is 0 feet per second, at time 1 is 2 feet per second, and at time 2 is 4 feet per second, and so on. So Cowpoke is speeding up. He just may catch that dream of his. Well, we say that t squared is an antiderivative of 2t, since 2t is the derivative of t squared.
Now, why is Cowpoke running? Well, he's chasing his dream, which is to be a cowboy. Unfortunately, that dream is staying 5 feet in front of Cowpoke. So the dream's position is always 5 more than Cowpoke's, or t squared plus 5. Even though Cowpoke and his dream have different position functions, notice that their speeds are the same because the dream speed equals the derivative of t squared plus 5, or 2t, which is also Cowpoke's speed. So we see that two things can have the same speed or velocity, but be at different positions. Here, both t squared and t squared plus 5 are antiderivatives of 2t. Poor Cowpoke.
Now, here's a couple of names and notations. In official calculus terminology, calcanometry and derivanometry. I'm sorry, there's that gibberish again. Another name for the general antiderivative is the integral, or more specifically, the indefinite integral. Now, there is such a thing as a definite integral, but we won't get into that now. But just you wait.
Okay, we have a special way we sometimes use to denote an antiderivative of a function. Instead of a lowercase f of x, we use a capital F of x to denote an antiderivative. Now, remember, an antiderivative is the opposite of the derivative. For a function f of x, we say its antiderivative is capital F of x. If we can then go backwards, taking the derivative of capital F of x and ending up with little f of x where we started. So, a capital F of x is an antiderivative of a little f of x if the little f of x is the derivative of the capital F of x.
If we're given a function, f of x, then its antiderivative is denoted by capital F of x. This also means that the derivative of capital F of x is little f of x. So, basically, if you have a function, f of x, and you take the antiderivative of it, you get capital F of x. Then, if you take the derivative of capital F of x, you will end up with the function little f of x that you started with. So, taking the derivative of the antiderivative puts you right back where you started.
As you can see, taking the derivative of the antiderivative gives you the original function again.
Now let's see what it means when we say any given function has an infinite number of antiderivatives. Well, suppose we have an antiderivative, capital F of x equals 2x squared plus 9. Using the power rule, the derivative of this is 4x. Now suppose another function, capital G of x, equals 2x squared minus 2. The derivative of this is also 4x. Notice that each function has a 2x squared but a different constant. Since the constant is eliminated when we take the derivative of the two functions is the same.
So, for our example, 2x squared plus 9 is an antiderivative of 4x, just as 2x squared plus 15 would be, or 2x squared plus 68, or 2x squared plus 193, or 2x squared plus 55, or...
All right, we get the point.
As you can imagine, there are an infinite number of constants we could use with 2x squared. In this way, there are an infinite number of functions whose derivative is 4x. This means that the function 4x has an infinite number of antiderivatives.
When you're talking about the infinite number of antiderivatives for a function, you don't call it an antiderivative anymore. The term indefinite integral is used when you're talking about all of the possibilities for the antiderivative and not just one particular expression. The term indefinite makes sense because with the indefinite integral, we're representing a lot of possibilities and not just one. If we had just one, that would be definite, now wouldn't it? More about that later. And don't forget the term indefinite integral is essentially another term for the general antiderivative.
Okay, let's go over the notation for the indefinite integral. Here's a sample function. First, we start with this wacky-looking swooshy symbol. This swooshy thing here is the integral symbol. After the integral symbol, you put the function you're integrating. In this example, we're using the function 4x. Next, we add a dx after the function. The dx just means with respect to x. So, this expression reads the indefinite integral of 4x with respect to x. So, in this example, f of x is 4x. The answer to this integral, or capital F of x, is 2x squared plus c. We'll show you how we got to that later, but first, a word about c.
We use the arbitrary constant, c, in the equation to represent any constant. We always add a c because there could be any number there and the derivative would still be the same. So, when we find the indefinite integral, we represent its generality by adding that c. Putting it all together, the indefinite integral of 4x is 2x squared plus c.
Section B. The rules of integration, or integration rules.
Now we're going to go through all of the basic rules for finding the antiderivative, a process better known as integration. The rules for integration were derived simply by reversing the basic derivative rules. Watch and see.
First, here's the general formula for integrating a constant. If we're integrating a constant k with respect to x, then the integral is the constant k times the variable x plus an arbitrary constant c. Don't be scared by the wacky symbol on the dx. It's just the notation for the antiderivative.
For example, suppose we want to integrate or find the antiderivative of the constant 3. Well, the integral of 3 with respect to x is just 3x plus c. It's pretty easy.
As you just saw, for constants like 2, 66, 89, negative 340, 8, pi, and so on, the antiderivative is easy. It's just the constant times x plus c, as you see here. But what about more complicated stuff?
Okay, now we'll give you the rule you use most often for the more complicated stuff, and it should seem familiar to you. It's called the power rule for integration, and it's the reverse of the power rule you use for the derivative.
The power rule for integration says that the integral of x to the power of n with respect to x is 1 divided by n plus 1 times x to the power of n plus 1 plus a constant. So the rule is to increase the power by 1 and divide by the new power, then tack on a constant, c. Let's put this baby to work.
For example, let's find the integral of x squared. N, or the exponent, equals 2. So, the integral of x squared is 1 divided by 2 plus 1 times x to the 2 plus 1 plus c. This simplifies to 1/3 x cubed plus c. Another way of saying this is x cubed over 3 plus c, because the 1/3 times x cubed simplifies to x cubed over 3 plus c.
Now, just to make sure, let's take the derivative of our answer to see if we get the original equation for which we're trying to find the antiderivative, which was x squared.
Use the power rule for derivatives, or n times x to the n minus 1 power. This equals 3 times 1/3 times x to the 3 minus 1 plus 0. Where'd we get the 0? Well, remember, the derivative of any constant is just 0, even if the constant is an arbitrary constant, c. This simplifies to x squared, so the derivative of 1/3 x cubed plus a constant is x squared, which is our original equation. Isn't it neat how that works out?
How about another example that's a little more complicated? Let's try taking the integral of 3x cubed plus 2x minus 4.
To do this one, we need to use the power rule for integration on each term separately. The first term is 3x cubed. Here, we take the integral of x cubed using the power rule for integration and then multiply it by the constant, or 3. The integral of x cubed is 1 over 3 plus 1 times x to the 3 plus 1. This becomes 1/4 times x to the 4th. So, the first term is 3 times 1/4 x to the 4th, or 3/4 x to the 4th. Now, we need to do the second term.
The second term is 2x. Again, using the power rule we learned, we'll leave the 2 and integrate the x. The integral of x is really the integral of x to the first power. Remember, anything to the power of 1 is itself. So the integral of x to the 1 power is 1 divided by 1 plus 1 times x to the power of 1 plus 1. Now we multiply by the constant 2. This simplifies to 2 over 2 times x squared, or just x squared.
The third term is just -4. Again, the integral of any constant is the constant times the variable x. So, since we are integrating with respect to x, the integral of this is -4x. Whenever you have a constant as part of an equation that you're integrating, the integral of that constant is just the constant times x. Constants are easy.
Now let's put all of these terms together. We get 3/4 x to the 4th plus x squared minus 4x, and don't forget the final constant, c. Why do we add a c at the end? Well, as we said earlier, any function has an infinite number of antiderivatives due to the fact that the derivative of any constant is 0. So to represent the infinite number of constants possible, you attach a c to the end. So, our final answer becomes 3/4 x to the 4th plus x squared minus 4x plus c.
Now let's try what appears to be a more difficult example. X squared plus 1, the quantity divided by the square root of x. Now I know what you're thinking. Let's just use the quotient rule for antiderivatives, right? Well, I'm here to tell you that there is no quotient rule for antiderivatives. In fact, there is no product rule for antiderivatives either. So we'll just have to find another way.
I told you there is no quotient rule for any derivatives, you tabloid freak!
Oh, yeah?
Yeah! Since we only have one rule, the power rule for integration, we have to adjust this expression algebraically so that our power rule applies. First, we can rewrite the square root of x as x to the 1/2 power. Then, we can bring it from the denominator to the numerator. When we do this, the sign of the exponent changes. So, 1 over x to the 1/2 becomes x to the -1/2 power. Now let's multiply this out to simplify it further. When multiplying the x terms, as you see here, you add the exponents. So, x squared times x to the -1/2 becomes x to the 2 minus 1/2, or x to the 3/2 power. 1 times x to the -1/2 is just x to the -1/2 power. Now, we can apply the power rule to integrate this, term by term.
For the first term, we get 1 over 3/2 plus 1 times x to the 3/2 plus 1. The second term is 1 over -1/2 plus 1 times x to the negative 1/2 plus 1 plus c. We simplify this and get 1 over 5/2 times x to the 5/2 plus 1 over 1/2 times x to the 1/2 plus c. Right here, we do a little cool algebra. Remember, to divide by fractions, you invert the fraction in the denominator and multiply by the numerator. So doing this, we get 2/5 x to the 5/2 power plus 2x to the 1/2 power plus c. That's the integral of our original function.
Let's quickly brush up on a couple of calculus terms you should be familiar with. We told you before that to represent the infinite number of antiderivatives that correspond to a single function f of x, we use the indefinite integral.
Again, this is the notation for the indefinite integral. This swooshy symbol is called the integral sign. The function f of x is called the integrand, and c is called the constant of integration.
Now that you've gotten familiar with the power rule for integration, there are a couple of trick rules you need to get acquainted with.
Let's try an example of the natural log trick rule. The integral of 1 over x, or x to the negative 1 power. Well, as we've said, this is one of the special rules. The integral of 1 over x, or x to the negative 1, is the natural log of the absolute value of x plus c. This is a tricky question your professor will probably spring on you, so be careful.
Now, what if you tried to do this the previous way without our new rule? Well, you'd be up the creek without a hot dog. You would apply the power rule for integrals, which would give you x to the 1 minus 1, or 0, power, divided by negative 1 plus 1. This would give you a 0 in the denominator, and we know, in the world in which we live, that you cannot divide by 0. You just can't do this problem without the special rule for natural logs. Now, how do we know this is the correct rule? Because if you remember, the derivative of the natural log of x is 1 over x. So again, the integral of 1 over x, or x to the negative 1, is the natural log of the absolute value of x plus c. Just memorize it.
Here's the integration rule for the exponential function, which is that e to the x thing we told you about earlier. Once again, this is something you'll just have to memorize.
This is really easy. If you remember, to take the derivative of e to the x, we left it as it was, just e to the x. Now, to take the antiderivative, we just do the same. Leave it as it is, except we add that crazy c.
Section C, the definite integral.
The definite integral is related to the indefinite integral. The difference is that the definite integral results in a real number value, while the indefinite integral represents an infinite number of functions using the arbitrary constant c. With the definite integral, you'll actually get a fixed number without the c for your answer. The definite and indefinite integral are related by a really slick fundamental theorem called the fundamental theorem of calculus. But we'll get to that later. For now, let's look at the definite integral in action.
For the definite integral, let's go back to that dreamer of ours, good old Cowpoke. When Cowpoke left his house to chase his dream, he was traveling 2t feet per second, so his velocity function was v of t equals 2t. His position function was given by an antiderivative of that, which was t squared. So using the position function, after 1 second, he was 1 foot from home. After 2 seconds, he was 4 feet from home. And after 3 seconds, he was 9 feet from home.
One way the definite integral is used is to find how far something travels during an interval of time. Let's see how far Cowpoke traveled from time equals 1 to time equals 3 seconds. We denote this by using the definite integral.
The definite integral uses the same swooshy symbol as the indefinite integral, but it adds a little number at each end of the symbol. Note the lower number is the beginning of the interval, and the higher number is the end of the interval. In our Cowpoke example, computing the definite integral is just like applying common sense.
So, Cowpoke's definite integral looks like this. We already know that at time 1, Cowpoke was 1 foot from home at s of 1, and at time 3, he was s of 3, or 9 feet from home. So, he traveled 9 minus 1, or 8 feet over the time interval from 1 to 3. So 8 is the definite integral of the Cowpoke example.
As you can see from the Cowpoke example we just went over, the definite integral applies to a function over a specific interval, from a to b.
In other words, geometrically speaking, the definite integral applies to the part of the graph of the function where x equals a is the left-hand endpoint and x equals b is the right-hand endpoint. If we look at the graph of a function, the definite integral of f of x from a to b applies to this part of the graph.
The function f of x is called the integrand, just like it was in the indefinite integral. The variable x is the variable of integration, and a and b are the lower and upper limits of integration, respectively.
So, the definite integral looks similar to the indefinite integral, except it is an integral of f of x over a specific interval with endpoints a and b. You can see how we represent this in the formula here. The definite integral of f of x from a to b equals an antiderivative of f of x, or capital F of x, evaluated at b, minus capital F of x evaluated at a. When we do definite integrals, we leave out the arbitrary constant c because it would just get subtracted out when we subtracted capital F of b minus capital F of a anyway. We'll see why all this works the way it does when we get into the Riemann sums and the fundamental theorem of calculus later on. But really, this setup is easier than it seems. It's just what we did with cowpoke earlier.
Now here's a real example of the definite integral. Let's find the integral of x cubed plus 8x minus 3 over the interval from 1 to 3. So our function, little f of x, is x cubed plus 8x minus 3. Now the first thing we need to do is integrate the function the same way we've been doing it for the indefinite integral. So we'll integrate x cubed plus 8x minus 3 term by term. The only difference is we do not add a constant c. Here goes.
Integrate each part using the power rule for integration. X cubed becomes 1/4 x to the 4th, 8x becomes 4x squared, and 3 becomes 3x. This is capital F of x because it's an antiderivative of little f of x. Again, we do not include an arbitrary constant c in our integration when computing the definite integral.
I'm here in front of Cerebellum Corporation, where the standard deviants have recently come under fire for refusing to use arbitrary constants in their calculus video. We tried to speak with the director of the calculus video, Joseph Doria, earlier today. Mr. Doria, I need to ask you a few questions about arbitrary constants. Just a few questions. Why aren't they in your calculus video, Mr. Doria? Mr. Doria, just a few questions, sir, please.
Thank you.
Just a few questions about arbitrary constants, sir. The people want to know. Tell me, why aren't they in your video, sir?
First of all, arbitrary constants will be in the video, and they're very important to calculus.
Mr. Doria, why do you hate arbitrary constants?
You people are all alike, you know that? This interview is over as of now.
So capital F of x is 1/4 x to the 4th plus 4x squared minus 3x. Now we want to evaluate this as a definite integral. In other words, we want to evaluate this over the specific interval from 1 to 3. To do this, we find a value for the antiderivative, capital F of x at x equals 3, and a value for capital F of x at x equals 1. Then, we subtract the value for x equals 1 from the value for x equals 3. In other words, we need to compute capital F of 3 minus capital F of 1.
We'll start by finding capital F of 3. To do this, all we need to do is substitute 3 for x into the expression for capital F of x. This becomes 1/4 times 3 to the 4th plus 4 times 3 squared minus 3 times 3. This simplifies to 189 over 4. Next, we'll find capital F of 1 by substituting 1 for x into the expression for capital F of x. This becomes 1/4 times 1 to the 4th plus 4 times 1 squared minus 3 times 1. This simplifies to 5/4. Now, all we have to do is subtract capital F of 1 from capital F of 3 to give us the final answer. So capital F of 3 minus capital F of 1 equals 189 over 4 minus 5/4, which equals 184 over 4, or 46. So the definite integral for this function from x equals 1 to x equals 3 is 46.
So what does this mean? Well, let's put it in a real-life example. Here's Matt Flanagan. He's an actual real-life person.
Suppose Matt Flanagan's velocity is given by x cubed plus 8x minus 3 feet per second, which was the original function we just played with, where x is time in seconds. After x seconds, the antiderivative capital F of x gives Matt's position function, or his distance from home. Capital F of 3 is Matt's position at time 3, and capital F of 1 is Matt's position at time 1. So the difference between them represents the net distance Matt traveled during this period of time. Matt traveled a net of 46 feet during that 2 seconds. By saying a net distance of 46, what we mean is that Matt is 46 feet further from home after 3 seconds than he was after 1 second.
So from this real-life example, we saw how the antiderivative can show the distance traveled by someone or something over an interval of time. Well, folks, let's hear it for our actual person, Mr. Matt Flanagan. Charlie, what do we have for Matt?
A copy of this video! Let's try another example. Say you're given the function little f of x equals 3 over the square root of x plus 4x cubed minus 6x. Integrate this function over the interval from 1 to 4. Again, we do this term by term, the same way we did with the indefinite integral, except we leave out the c because, as you know, there are no arbitrary constants needed with the definite integral.
The first term looks scary until we write it another way. Whoa, down boy! But looky here! 3 over the square root of x can be rewritten as 3 times x to the negative 1/2 power. Remember, 1 over the square root of x is just x to the negative 1/2 power. Now, using the power rule for integration, this integrates to 6 times x to the positive 1/2 power.
The next term, 4x cubed, integrates to x to the 4th. And the last term, negative 6x, integrates to negative 3x squared. Putting these terms together, the integral of 3 over the square root of x plus 4x cubed minus 6x becomes 6x to the 1/2 plus x to the 4th minus 3x squared. So this is our capital F of x.
Now, we want to evaluate this over the interval from 1 to 4. So we need to find the values for capital F of 1 and capital F of 4, and then subtract the value capital F of 1 from the value capital F of 4. It's just that simple.
Subbing in to capital F of x, capital F of 1 equals 6 times 1 to the 1/2 plus 1 to the 4th minus 3 times 1 squared. Remember that anything to the 1/2 power is the same thing as taking the square root, so the first term would be 6 times the square root of 1, which is just 6 times 1, or 6. The second term is 1, and the last term is negative 3. So we have 6 plus 1 minus 3, which is 4. Capital F of 4 equals 6 times 4 to the 1/2 plus 4 to the 4th minus 3 times 4 squared. Simplifying this, we get 12 plus 256 minus 48, or 220. So capital F of 4 minus capital F of 1 equals 220 minus 4, or 216. So our final answer is 216. Section D, Riemann sums.
Okay, let's slow down and get philosophical for a few minutes. We're going to try to get to the bottom of why this integration stuff works. To begin, we need to understand something called Riemann sums. To explain Riemann sums, we'll go back to cowpoke. We were given that cowpoke's velocity is represented by the function v of t equals 2t. We use this and the definite integral to find the actual distance cowpoke traveled during the first 3 seconds, from time 0 to time 3.
Now, to estimate the distance cowpoke traveled during those 3 seconds, we could reason this way. Remember that cowpoke was speeding up during those 3 seconds, so we can't just use his ending velocity to calculate his distance traveled. We need to break that time period down and calculate his distance traveled over a few intervals to better estimate his total distance traveled.
Since distance is velocity times time, we can estimate cowpoke's distance traveled over a few intervals by first finding his approximate velocity in each interval and multiplying by the time. First, we need to estimate his velocity, which is given by v of t equals 2t. At time 0, his velocity is 0 feet per second. At time 1, his velocity is 2 feet per second. At time 2, his velocity is 4 feet per second. And at time 3, his velocity is 6 feet per second.
To approximate the distance cowpoke traveled during each 1-second interval, that is from time 0 to time 1, from time 1 to time 2, and so on, we will multiply his velocity at the beginning of that interval of time, times the length of time of each interval, 1 second in this case. So from time 0 to time 1, cowpoke travels approximately v of 0 times 1, or 0 feet. From time 1 to time 2, he travels about v of 1 times 1, or 2 feet. And from time 2 to time 3, he travels about 4 feet. So, if we add these distances together, the approximation of the distance he has traveled is 6 feet. If you wanted the exact distance he traveled, you would take the definite integral over the entire interval of cowpoke's time, or from 0 to 3 seconds.
The Riemann sum is essentially the sum of all those approximations. Now, the actual distance he traveled is the definite integral from 0 to 3 of 2t, which we determined before to be 9 feet. So, our approximation of 6 is not very good.
To improve our approximation, let's try increasing the number of measurements by reducing the size of each interval to 1/2 second. If we break it down into intervals of 0 to 1/2, 1/2 to 1, 1 to 1 and 1/2, 1 and 1/2 to 2, and so on, we get as our approximation 7.5 feet, which is better but still not accurate. Here we found cowpoke's velocity at the beginning of each half-second interval of time, then multiplied this velocity by 1/2 second to get the approximate distance traveled during each half-second. If we keep picking smaller and smaller intervals, our approximation will get closer and closer to the actual answer of 9. For instance, if we were to go through this whole process again for intervals of 1/10 of a second, we would get an approximation of 8.7 feet. And this is a much better estimate because earlier we found the answer to be 9. To understand what's really happening here, let's look at the graph of cowpoke's trip.
Each interval is represented by the area of a rectangle underneath the curve. The graph for our approximation of 6 shows why this is not a very good approximation. The rectangles, or Riemann sums, are too coarse. There's a lot of space that's getting left out. However, looking at the graph with smaller and smaller intervals, we can see how the approximation gets closer and closer to the actual answer. The smaller your intervals using Riemann sums, the better your approximation. The actual answer, or in cowpoke's case, the true distance he travels, is just the limit as the base of the rectangles go to 0, or the limit as the length of the intervals of time go to 0. This is the actual definition of the integral from 0 to 3 of 2t in our case. Got it? Riemann sums crystal clear? No? Well, let's review what we've done in generic terms. Let's talk x's and f of x's instead of t's and v of t's. Let's say we have a function, f of x. What we just did was we tried to estimate a definite integral from x equals a to x equals b of f of x by breaking the interval ab into smaller subintervals. We can call the length of each subinterval delta x. The delta symbol looks like an itty-bitty triangle. These subintervals break the area under the curve into a series of rectangles.
We found the approximate area of each subinterval by multiplying the beginning height, or y value for that interval, times the length of that interval, delta x. Area of a rectangle, base times height. Get it? To get our final answer, we then added all these approximations together to get an estimate for the entire interval.
As the lengths of the intervals get smaller, from 1-unit intervals to half-unit intervals to 10th-unit intervals, our estimates get better. As the length of the intervals delta x goes to 0, our estimates go to the actual answer. This sum is called a Riemann sum. As complicated as it is, this also happens to be the definition of the definite integral. So, the definite integral is just the limit of a Riemann sum, which is an approximation of area, as the length of each subinterval, or base of each rectangle, delta x, gets smaller and smaller, or approaches 0. This equation is the mathematical shorthand for all of this. I know it looks really complicated, but for your class, all you really need to know is how to compute these sums like we did earlier with cowpoke.
Section E, the fundamental theorem of calculus.
E is the magic section. Magic.
This theorem grows out of everything we've been doing up to this point. It's actually nothing new. It's just that without understanding Riemann sums, we couldn't cover it. Now that we have Riemann sums down pat, here goes the theorem.
The fundamental theorem of calculus says that if f of x is continuous on the closed interval ab, and capital F of x is any antiderivative of f of x on that interval, then the integral from a to b of f of x is just the antiderivative evaluated at x equals b minus the antiderivative evaluated at x equals a.
The fundamental theorem says that if the function f of x is continuous, then the limit of that messy Riemann sum exists, and that limit can be found by doing antiderivatives. just like we did before. Thus, it tells us we don't have to compute those messy sums. We can do it the way we've been doing it throughout this video. I know this seems rather anticlimactic, what with this being a fundamental theorem and all, but we've been using it to compute definite integrals for the last 30 minutes.
As a word of caution, you may not be able to actually find an antiderivative of f of x in some cases. Then, we may actually have to compute those messy sums since we can't apply the fundamental theorem of calculus. But that's a story for another day.
Finally, for summary, the fundamental theorem just says that the areas or distances obtained by using Riemann sums can be found more easily by using antiderivatives, just like we've been doing. So give yourself a pat on the back. You're a mathematician and you didn't even know it.
Section F, area. Now we can look at the definite integral geometrically speaking. Geometrically speaking, as we've seen from the Riemann sums, the definite integral can represent area. The definite integral of a positive valued function equals the area between the curve of the function and the x-axis, from x equals a to x equals b, as you see here. A positive valued function is just a function whose graph is above the x-axis, like this one.
Let's say Summer Powers is out doing a little cross-country skiing. Her velocity is given by 3t cubed minus 15t squared plus 18t. Notice that her velocity is 0 at t equals 0, 2, and 3, so she stopped for a split second at these points as she changes direction. We can also see that she speeds up during the first second, then she slows down and stops at time 2, then she reverses her direction and stops again at time 3. The distance from home she's traveled at time 2 is equal to capital F of 2 minus capital F of 0, which turns out to be 8 feet.
Why 8 feet? Well, as you can see here, we took the integral of f of t, or the original function, and got 3/4 t to the fourth minus 5t cubed plus 9t squared. Then we inserted 2 for time t equals 2 seconds, and got 8. Then we inserted 0 for time t equals 0 seconds, and then we subtracted the 2. That's how we got 8 feet at time 2.
But to find the distance Summer is from home at time equals 3, we find capital F of 3 minus capital F of 0, which is 6.75 feet. How'd we get a distance of 6.75 at time 3? Just insert 3 into the function. You get 3/4 times 3 to the fourth minus 5 times 3 cubed plus 9 times 3 squared. This equals 60.75 minus 135 plus 81, which equals 6.75.
But if Summer was at 8 feet at time 2, how could she be at 6.75 feet at time 3? Well, the reason she is closer to home at time 3 than at time 2 is because she traveled backwards between time 2 and time 3. In fact, the distance she traveled backwards is equal to capital F of 3 minus capital F of 2, which equals negative 1.25 feet.
At this point, there are several questions we could ask. Does your deodorant chafe you? Is your right foot slightly larger than your left? Do you find nose hair to be a serious problem? But more importantly, after 3 seconds, how far is Summer from home? Well, we know the answer to that is 6.75 feet. But another question we could ask is, just how far did Summer ski overall?
To answer this question, we must first find how far Summer skied forward and add it to how far she skied backward. It is vital that we distinguish her direction at all times. She skied forward when she has positive speed, or when f of t is above the axis. This is from time 0 to time 2. Just a moment ago, we already found this distance to be 8 feet.
Then we have to compute how far she skied backwards. This is when the velocity is negative, or f of t is below the axis. We already found this to be negative 1.25 feet. Now, we know that distance can't be negative when we are looking at the total distance traveled, as opposed to distance from the starting point. So we take the absolute value of these distances to come up with total distance, regardless of which direction Summer was heading. So the total distance she skied is the absolute value of 8 plus the absolute value of negative 1.25, or 8 plus 1.25, which is 9.25 feet. Not much of a skier.
Another way we can answer this question is with area. Remember when we said that the definite integral can equal area? No? Well, here, watch this.
The definite integral can represent area. The definite integral of a positive valued function equals the area between the curve of the function and the x-axis from x equals a to x equals b, as you see here. A positive valued function is just a function whose graph is above the x-axis, like this one.
Back to Summer. If we convert her velocity function over to x's instead of t's, we have 3x cubed minus 15x squared plus 18x. Now, to find the area between this curve and the x-axis, there are two regions whose area we must find. Looking at the graph, we see that the first region is from 0 to 2 because that is where the graph is entirely above the x-axis. The second region is from 2 to 3 because that is where the graph is below the x-axis. So, the area between the graph of 3x cubed minus 15x squared plus 18x and the x-axis from 0 to 2 is this integral, which is 8 square units. The area from 2 to 3 is given by this integral, which is negative 1.25 square units. It's negative because the graph is entirely below the x-axis.
Now, to get the total everyday positive area, you must compute the areas above and below the axis separately. We then take the absolute value of each, because area can only be positive, and add them together. Doing this, we get 9.25 square units. So the area bounded by the curve is equal to the total amount Summer skied, but in different units.
Let's try another example to get this area stuffed down to down. Let's find the region bounded by y equals x cubed minus 4x and the x-axis.
First, we'll graph the function to get an idea of what it looks like. Notice there is one area above the x-axis and one area below the x-axis. We'll need to integrate this in two parts. You'll see why in a second.
Before we can integrate this, we need to determine where the curve crosses the x-axis. This will tell us the endpoints for our intervals. To find these endpoints, we need to set the function equal to 0 and solve for x.
We set x cubed minus 4x equal to 0. This factors into x times the quantity of x plus 2 times the quantity of x minus 2. So for this equation to equal 0, x must equal 0, negative 2, or 2.
We can see from the graph that the region from x equals negative 2 to 0 is above the x-axis and the region from 0 to 2 is below the x-axis. So, we'll integrate separately from negative 2 to 0 and from 0 to 2. We'll call the area from negative 2 to 0 area A, and we'll call the area from 0 to 2 area B.
If the function falls below the x-axis, we get a negative value for the area. However, as a general rule, everyday area can only be positive. You can't have negative area. Unless maybe you live in a bizarro world. In that case, all you'd have would be negative area. But since we don't live in a bizarro world, we can't have negative area.
Our first step is to find where the function intersects the x-axis, which we already did. Then, we integrate the function above the x-axis and the function below the x-axis as two separate integrals over the corresponding intervals. Finally, we take the absolute value of the area below the x-axis and add it to the value of the area above the x-axis to get the total area between the curve and the x-axis.
To integrate separately, our problem becomes the integral from negative 2 to 0 of x cubed minus 4x, plus the absolute value of the integral from 0 to 2 of x cubed minus 4x. Again, we take the absolute value because we know that the second integral of the function is negative over this interval. But we need to know the area it represents, so we use the absolute value.
First, we'll get the integral of the function. Integrating x cubed, we get 1/4 times x to the 4th. Integrating negative 4x, we get negative 2x squared. So our integrated function, capital F of x, is 1/4 x to the 4th minus 2x squared. Here are our two original integrals again. Area A is from negative 2 on the bottom to 0 on the top. Remember, when doing an integral, we subtract the value at the bottom from the value at the top. And since we're doing area, we take the absolute value. So we take the absolute value of capital F of 0 minus capital F of negative 2. Capital F of 0 equals 1/4 times 0 to the 4th minus 2 times 0 squared, which equals 0. Capital F of negative 2 equals 1/4 times negative 2 to the 4th minus 2 times negative 2 squared, which equals negative 4. Then the absolute value of capital F of 0 minus capital F of negative 2 equals 0 minus negative 4, which equals the absolute value of 4, or just 4. So area A equals 4 square units.
Area B is evaluated from 0 to 2, so we need to find the absolute value of capital F of 2 minus capital F of 0. We already know that capital F of 0 equals 0. Capital F of 2 equals 1/4 times 2 to the 4th minus 2 times 2 squared, which equals -4. Then the absolute value of capital F of 2 minus capital F of 0 equals the absolute value of -4 minus 0, which equals 4. So area B equals 4 square units. The total area equals area A plus area B, which equals 4 plus 4, or 8 square units.
So the area of this graph, both above and below the x-axis, is equal to 8 square units. In this example, area A and area B were the same. If we had realized the graph had a nice symmetry, we could have saved a lot of rework and just multiplied the first area by 2. Be careful though, this doesn't always happen. Now let's look at a super difficult, impossible to solve problem. Let's see if we can find the area between the two curves represented by these functions. F of x equals x cubed and g of x equals 4x. Here's what this looks like graphically. What we're looking for is the area of the shaded portion.
Sounds pretty impossible, huh? Well, what if I told you we just did this problem? Would you believe me? Would you run away? Well, we did just do this problem. Here's how. The key is to know that the area between two curves, f of x and g of x, is the same as the area between the curve f of x minus g of x and the x-axis. This works no matter how complex the functions are. In this case, they are relatively simple.
So, finding the area between f of x equal to x cubed and g of x equal to 4x is the same as finding the area between x cubed minus 4x and the x-axis. We just found that area. So the area between f of x and g of x is also 8 square units. Even though the graphs and regions don't look the same, the amount of area is the same. Don't question it. This is just something you have to accept.
So whenever you need to find the area between two curves, just subtract them and find the area between that new curve and the x-axis. For example, to find the area between the curves f of x equals x cubed plus 14x and g of x equals 9x squared, we only need to find the area between the function h of x, which equals f of x minus g of x, and the x-axis. So, h of x would be x cubed plus 14x minus 9x squared. This can be written as x cubed minus 9x squared plus 14x. We won't go through the rest of the problem, since it's just like the area problems we already did. But really, it's straightforward.
Section G. Substitution and change of variables.
Finding derivatives was easy because we had several clear-cut rules, such as the product rule, quotient rule, and chain rule. Antiderivatives are more difficult because there is no direct product rule, quotient rule, or chain rule counterpart.
When faced with finding the antiderivative of the product of two functions, you have to try something different. We'll describe two methods that may work. There are many other methods to try if these two don't work, but you'll only need to learn those if you take a more advanced calculus course. For now, we'll stick with the two most common methods. The first method is simplifying. The second method is substitution or change of variables.
First, we'll do simplification. Suppose we want to integrate the quantity x plus 3 times the quantity x squared minus 2. Since there is no product rule, we must try something else. The easiest thing to try is simplifying. We can multiply this out. Now, this is much easier to integrate. Using the power rule for integration on each term, this integrates to 1/4 x to the 4th plus x cubed minus x squared minus 6x plus c. Notice that our arbitrary constant c is back because we're taking the indefinite integral here. So, the first method is to simplify the function by multiplying it out and then integrating it with the power rule for integration.
Now let's look at another, more complex problem.
Let's say we've got x cubed times the square root of 2x to the 4th minus 7. Again, there is no product rule for integrals, but this time we can't simplify the function by multiplying it out either. So here's the second method, substitution